Hi everyone. I thought I'd make a series of videos to help people out in terms of stoichiometry because it comes up twice in terms of VCE chemistry, or twice specifically, but really it's just throughout Unit 2, 3 and 4 chemistry. And realistically you can't really do any maths and chemistry without knowing how to do stoichiometry. So I thought I'd go through a, a series of PowerPoints that I'm kind of proud of. I can't say it's all my idea. I got most of this idea in terms of a way to represent stoichiometry visually with a box from a research paper a few years ago. I think it was called Bill's box at the time. And I've just applied it to a specific scenario here. So hopefully the analogy that's kind of is carried out through this is helpful in terms of understanding stoichiometry. So I'm going to be talking a lot about bikes because obviously bikes and chemicals are basically the same thing. Oh, hopefully you'll see how that's the case. So, got a scenario here. I've decided that teaching doesn't really make enough money. It's not lucrative enough, rising costs of living, stuff like that. Got to afford your mortgage. So I've decided to open up a bike factory instead. So I'm going to use some equations to represent making the bikes, and we need to make sure that we're buying the right amount of parts. So we're going to use an equation to help us with that. And so when we make a bike, all right, it's got a frame and it's got two wheels. So we can write that as an equation. We can write that as there's a frame and two wheels makes a bike. So in red we've got the frames, in blue we've got the wheels, and in green we've got the bikes. You can see that the formula for a bike is a frame and two wheels as given by our symbol there. So if we want to make more than one bike, how can we do it? So if we've got 6 frames, how many bikes could we make? Well, we can look at the ratio that's here, and we can say, well, if for every one frame we have, we can make one bike. That's what the number at the front means. So another way we could write that is that we've got to start with 6, and we can times it by the number we're going to and divide by the number we're coming from. Or you can think about it as a ratio. There's a few different ways we can think about it. As a 1-to-1 ratio of frames to bikes. So therefore, the number of bikes is going to be equal to the number of frames. So we can go ahead and say, well, if we've got 6 frames, we could make 6 bikes out of those 6 frames. Now, we can also go the other way as well. If we want to make 21 bikes, how many wheels are we going to need? So we can have a look at these coefficients at the front again, and we can see that again two ways we could think about this. We could multiply it by the number we're going to, so we're coming from a 1 and going towards a 2, so we can multiply it by 2 over 1, and that'll give us an answer there. The other way you could look at it is you could say there's a 2-to-1 ratio of the two numbers here. There's twice as many wheels as there are bikes, so if we've got 21 bikes, therefore there must be 21 times 2, or 42 wheels. So we've got 42 wheels there. So in these cases here, if we know the amount of one of them here, the only information we need to know is the ratio. The other thing to point out is if we know the number of bikes, we can also find the number of frames. Well, if we've got 21 bikes, there's a 1-to-1 ratio, so there'll be the same number of frames as bikes. So we could say there'll be 21 frames. So if we know one value, we can find every other one along here. So in terms of connecting this to Unit 2 chemistry, which is where this is first introduced, you need to be able to do mass stoichiometry for this topic here. And you should be able to do a little bit of volume stoichiometry. So that's just saying going from a mass to another mass or a volume to another volume. And basically the essence of stoichiometry is, can you find an amount of a product or reactant if you have another one? So connecting the bike analogy there to chemistry, in the bike analogy, if we knew how many of bikes or wheels or frames or whatever, so basically a part of a bike or the final number of bikes, we could find all the other numbers of things that we needed. So the same thing is true for chemistry. If we know the amount, so the mole remember anytime we say amount in chemistry, we're referring to mole. If we know the mole of one reactant or product, we can actually find all of the other ones that would be needed to produce it or would react with it or anything like that. And so I've written this in an equation form here. If you like using ratios, by all means, just think about things in terms of ratios. In terms of an equation, you can write it like this, which it might look complicated, but it's literally what I just did with the bikes, where we said, okay, we're multiplying by, we've got our amount of whatever. To find the amount of something else, we multiply it of the thing we're going to, and we divide it by the coefficient of what we're coming from. So for example here, we've got 1 mole of nitrogen gas and it's reacting with hydrogen. How many mole of ammonia would be produced? So remember that there's assumed to be a 1 if there's nothing written in front of a chemical. We've got 1 mole of nitrogen gas, and we're back. And to get to ammonia, we can times by 2 and divide by 1. Again, the other way you can do that is you can say, well, there's a 2-to-1 ratio or a 1-to-2 ratio there. There's twice as much ammonia as there is nitrogen. Now, if you've got 1 mole of nitrogen and there's twice as much ammonia, well, then there must be 2 mole of ammonia, which is the same as 1 times 2 over 1. And we can go the other way as well and say, how much hydrogen gas would we need to make 2.7 mole of ammonia? So we can say 2.7, let's times it by 3, divide it by the 2. 2.7 times 3 over 2 is going to be 8.1 over 2, so 4.05 mole there, I'm pretty sure. Again, you could do the same thing with ratios and say it's a 3-to-2 ratio, so there's going to be 1.5 times as much hydrogen as there is ammonia. 1.5 times 2.7 is going to be 4.05. So all of that is, if you can do that, you can already do stoichiometry, right? So stoichiometry, that's really the only new thing to stoichiometry if you already knew how to do amount calculations. So it's just, once you have a mole value, can you find the mole value of something else? And that's just using the mole ratio. That's all there is to it. And so there's a chem quiz for this. So they're really good for being at randomly generating numbers and giving you some practice there. If you put the moles as units, you'll get some simple ones like this to start off with. So, obviously we can calculate how much when we've got a small amount of our frames or our wheels there, but what happens once we want to actually start making a bunch of bikes? So rather than buying an individual frame or an individual wheel from a factory, we're going to buy some crates. So we've got our same equation, but we're going to buy some crates so that we can get a bunch at the same time. So when we buy a crate of frames, let's just say that each crate contains 30 frames. So that, again, this is basically a ratio, right? So we're saying one crate has 30 frames. Well, there's a 1-to-30 ratio of the crates to the frames. And if we've got a crate of wheels, it's got 100 wheels in it. Okay. So what can we do with this? Well, if we know how many crates, the frames or wheels there are per crate, we can convert between that number of crates and the number of different things we've got going on there. So if we've got 40 crates of frames and 20 crates of wheels, we could calculate how many of each we have. So we've set up this nice table here which has the number of crates, how many things there are per crate, and the total number of frames or wheels or bikes or whatever. So we've got 40 crates of frames, and we've got 20 crates of wheels. So if we've got 40 crates of frames, and each crate has 30 in it, altogether we're going to have 1200 frames, right? So 30 times 40. If we've got 20 crates of wheels and each crate has 100 in it, we could just say, well, there's 2000 wheels in it. So you can see how the count there, how many there are per crate, is just the ratio between this and this. Or the way we've set it up is if you times the top two, you'll get the bottom one. So let's say a school has given us 3 spare crates of frames. Alright. How many crates of wheels do we need to buy to turn all of the frames into bikes? So we've got 3 crates, and there's 30 frames per crate. So overall, we're going to have 90 frames. Now, from this, if we know how many frames there are from before, we actually also can figure out how many wheels we have, or we're going to need. If we have 90 frames, there's a ratio of 1 to 2, or again, you could multiply it by 2 over 1. We're going to need 180 wheels to combine with the 90 frames. And then, now the question here is asked how many crates we're going to need. So if we've got 180 wheels, and there's 100 in each crate, how many crates do we need? Well, it'll be 180 divided by 100, so we'd need 1.8 crates there. Please stop me if you want to have a go at these before I go through the answer. And how many bikes will we be able to make? Now, we can go from the 90 to the we can go from the frames to the bikes, or we can go from the wheels to the bikes. They will actually give us the same answer because it's all, again, just a ratio. Let's just go from frames. So if we've got 90 frames times 1 over 1, or we could say it's a 1-to-1 ratio, so there'll be 90 bikes as well. So from these 3 crates donated, we'll get 90 bikes altogether. But we'll need to buy 1.8 crates of wheels. Alright, so we've got a big order, and New Zealand wants to buy 5 crates of bikes to do with their tourism industry, I'm sure. So each crate of bikes has 15 bikes in it, and they want 5 crates. So how many crates of frames will we need to order? And you'll notice there's a trend with most of these questions in terms of the box that we've made. We usually get given a value up the top, and we're going to need to go down, across, and then up. And that basically is what we're going to see for any possible stoichiometry. So we've got 5 crates. Each crate has 15 in it. So altogether we're going to have 5 times 15, which is 75. Now if we've got 75 bikes, what's our ratio? Well, it's 1 to 1, or we could times what we're going to, divide by what we're coming from. So we're also going to need 75 frames. If we need 75 and there's 30 per crate, 75 divided by 30 is going to give us 2.5 there. So we're going to need to have 2.5 crates. Now you might say, how can you buy half a crate? Well, it is true that you'd need 2.5 crates. You might say, but you'd need to buy at least 3, and that is that's a great question to ask. That is its own separate topic of limiting reagents that we'll get to later. So we can tell that there's 2.5 crates there. How many crates of wheels? Well, again, if we've got 75 here, times 2 over 1, or 2 to 1 ratio, we'll need 150 wheels. If there's 100 in each crate, then there'll be 1.5 crates of wheels needed there. So we'll need 2.5 crates of frames and 1.5 crates of wheels to be able to make those 5 crates of bikes. Alright, so linking that back to chemistry, we can do a pretty similar thing here and set up a table with mass at the top. So we're going to start with mass stoichiometry, and amount down the bottom. Now we already saw that it's really easy to do the ratios. So we can, as soon as we have any amount in a reaction, we can find every other amount value that's there. And this is what stoichiometry is, by the way. And so our top row, we can have mass. Concentration can work there as well. And then if we want to convert between mass and amount, hopefully you're familiar with this equation here that's in the data book. And this is what I meant before in terms of if you can convert between the mole at the bottom here, you already know all the new stuff for stoichiometry. The only other thing we're going to do is we're going to move up and down in the columns by using this equation that you already know how to use. So in this case here, we're going to use this put the second row as the molar mass, because molar mass really, all it is a ratio. So when we say that carbon has a molar mass of 12 grams per mole, that's a ratio, isn't it? It's just saying if you have 1 mole, you have 12 grams. In a similar way to saying if you had 1 crate of wheels, we have 100 wheels. So there's just it's just a ratio here. So in this case here, whereas we kind of multiplied to go from the top to the bottom with the crate example, in this case here, we divide by the molar mass. So if we've got a mass and we want to find an amount, we divide by the molar mass. So if we just plug that into the middle value there, we can divide that through. And so remember, most of our calculations are just going to be down, across up. So it's going to be divide by molar mass times by the ratio and then multiply by the other molar mass. And that's it. And that's all of stoichiometry. Alright, so here's the Haber-Bosch equation again. Here's an example. We've got 57.3 grams of nitrogen gas. I've said there's excess hydrogen gas, so we know the nitrogen is going to run out first. How much ammonia can we make? So we can identify what we need to find first. We want to find this value. And you should, as long as you know what chemicals there are, which you do 98% of the time, like it's only if VCAR decides to give you a question that's like, oh, there's an unknown chemical, but when you react 1 mole, it makes 3 moles. Every other time you're going to know what the chemical is. So we can plug in our molar masses here. So we know nitrogen gas is 28. Make sure you don't put 14 in because it's nitrogen. It's nitrogen gas. 2 nitrogen atoms is 28. And ammonia is going to be 17. So 14 from the nitrogen and 1 from each hydrogen. So to find our, remember we're going to go down, across, then up. So all we need to do is take our 57.3, divide by 28, times by the ratio, which is going to be times 2 over 1, and then multiply by 17. So you can even you can actually just jam all of that into a calculator together and get the final value. Now I like to do it one step at a time so that you don't stuff anything up. So for example, this is 2.046. I'll mention sig figs in a second. Times 2, 4.09, and then times 17. Now make sure you don't round off during this process, so don't try. You can round it off while you're writing it, but don't round it off in your calculator until you get the final answer. So my final answer on the calculator is 69.57857. Obviously that's too long. We've got 3 significant figures in the original question, so I will round this to 3 sig figs, which puts it at 69.6 grams. And we can look at that to give us like and roughly guess, does that value make sense? Now, we make twice as much ammonia as we had nitrogen, but the ammonia is a bit lighter than the nitrogen. So I'd expect it to be in between 1 times and 2 times the mass of nitrogen, and that's what we get there. So if I looked at that value and it was like 200, that wouldn't really make any sense. Also, if it was 20, that also wouldn't make any sense. 69.6 seems like a reasonable value to get out at the end. So being able to estimate things is really useful for any maths type work, but it's particularly useful for chemistry and physics as well, because a lot of the time you're working with very sensible numbers. If you've made a product in the lab, if you're answering a question and your calculation says that you made a ton of product in the lab, you're probably wrong, or the lab just exploded. So either one of those, probably not great. So, and just to point out here, so I've done it there in terms of the ammonia. We could also have found the mass of the hydrogen as well. So as soon as you have, when you're doing mass stoichiometry, as soon as you have any mass value, you can find the mass value of every other reactant and product in the equation, because you will know all the molar mass values from the periodic table. So the other thing to do is make sure you don't try and use the mole ratio to convert between masses. That doesn't work. So you can't just say, oh, well, there's 3 times as much hydrogen, so it's going to weigh 3 times as much. That's not accurate. You're right that there is 3 times as much, but each hydrogen weighs, 1/14 of the mass of one nitrogen molecule. So we could say, take this, divide it by 14, and multiply it by 3, but that's exactly the same as doing what we did. Divide by 28, times by 2, 28. 2 over 28 is going to be dividing by 14 anyway. So that's the same thing there. One thing you can test if you're really unsure is that the mass values of the reactants will add up to the mass values of the products. So in this case here, 57.3 and 12.3 together add up to 69.6. If you're really uncertain for some reason, or you want another way to double check your answer, you could figure this out. Another, I guess, way that this could maybe save you 30 seconds on an exam is if you start with this one and you need to calculate both of these. Once you've found one of them, you can actually just find the other one by either adding them together or subtracting one from the other. Note that it's going to get harder and harder to actually use that as a trick as you get more chemicals though. If you've got two reactants and two products, you're probably not going to find two other values just so that you can find the third one. Just go and find the third one in the first place. Okay, in terms of concentration, we can do something similar, but we're going to use a different equation. So the main thing when we're using a box like this is to keep in mind, keep the mole on the bottom row. So if you so basically the one thing you need to remember is only use ratios for amounts, don't use it for masses or concentrations. So in this case here we can put concentration and our volume in, and if we've got those two, hopefully you can remember the equation that compares all of these is C equals N over V, or we might like to rewrite that. That's how it is in the data book. N equals C times V. So if we've got a value here, we can multiply the top and the middle to get our amount there. Alright, so a lot of the time you'll get a question and there's a bunch of numbers in it like this, and we want to spot where we can chuck them in. Obviously right now I didn't actually have a question. So calculate the concentration of the sodium hydroxide. So we want to find this. We've been told the volume of sodium hydroxide, so this is going to be, remember we want to put it in liters, so 0.25. We've been told we have 0.53 mils of hydrochloric acid, 0.53 liters, sorry, and that the concentration of hydrochloric acid is 0.21. Now, once you've laid these all out, so note that one thing you'll notice is different is that we could just look at the periodic table and we'd know every single one of these values in the middle. You have to be told the volume if we're going to be doing it for concentration. And you might recognize these types of calculations from volumetric analysis. Now, once you've put these in, the really easy way to, again, all we're going to do is go across, down, across, and up. The other way you can tell what you want to do, or what you can actually find, because sometimes you'll be given a whole bunch of different values. So we could be given the volume of the sodium chloride and the concentration of water. Not that that would really do anything. They wouldn't be very useful. What's useful is when we have two values in the same column. So in this case here, the hydrochloric acid, we know both the concentration and the volume. So we know this, and we know this. And once we know both of those, we can multiply them together. Times 0.53, and we can say 0.1113 is our amount there. Our mole ratio is 1 to 1, 0.1113. That looks like a negative now. If we've got our amount and our volume, you should know that the concentration is going to be amount over volume. So we take our amount, divide it by 0.25, and lo and behold, we get 0.4452 molar. In terms of sig figs, we've got 3 here, we've got 3 here, and we've got 2 here. So we're going to round it to 2 significant figures, which will round it off to 0.45 mole per liter. If we want the concentration of the final sodium chloride solution, again, it's a 1 to 1 to 1 ratio, 0.1113. Now you might say, what's the volume here? Now we know we had 250 mils and we mixed it with 530 mils. So together these add up to 780 mils, or 0.78 liters. So again, we can take our amount, which is 0.1113, and divide it by 0.78, and we're going to get 0.14269, or we're going to round it off to 2 significant figures, so 0.14. And we could also find the mass here, and this is where the box starts to struggle a bit. If you're trying to use different values in here, we can go across to the mole ratio there again. But in this case here, because we're looking for a mass, we'd need to multiply it by mass. And this is where it gets a bit tricky, where this middle value here, you kind of have to use different things. So I will put a video out looking at some different ways we can represent that. It starts struggling a bit once we get into that position there. and we can put that in, and we get it's about 2.0 grams. Remember to put that decimal there to finish that off. Okay, now I've got one question here that should finish off these examples. So what mass of barium sulfate is made when we mix these two here? So we've got barium sulfate. Now you should be able to write an ionic one as well. Sodium sulfate. What are they going to make here? Oh, sorry, barium nitrate. So normally you wouldn't be given a specific box here, but you can draw yourself up one here. So something like that. That was really bad. If you want to do this in a test, bring a ruler. So remember we had concentration, volume, amount. Doesn't need to be beautiful. So we've got 100 mils of 0.152 of the barium nitrate. So we've got 0.1 liters, 1.52. We're looking for mass here, so we're going to use the molar mass. And I'm going to grab a data book quickly, because I don't remember barium off the top of my head. 137.3. So barium is 137.3, sulfur is 32.1, and oxygen is 16, so that's 64. So overall this is going to be 233.4 grams per mole. And as soon as you've got this, you should be able to say, alright, we've got a concentration and a volume. The concentration times the volume is the amount. And hopefully you can multiply it by 0.1 in your head, 0.152. The ratio is 1 to 1, so the ratio is 0.152 there. And then we're going to multiply by the mass to get, or the molar mass, sorry, to get our final mass here. 35.4768. We've got 3 sig figs in the original question, so we're going to go 35.5 grams. So that should be enough to get you started on anything for stoichiometry. You can have a go at the chem quiz and things like that. Let me know if you've got any questions.